if we think about the Lagrange function as sort of a penalty-based system, it really, I think, makes sense why we construct it the way we do. Recall that the Lagrangian from an objective function, which we call f of x, and its constraints, so we could have g I of x where I goes from 1 to say m. So if m is 10, that means we have 10 constraints, and each constraint is going to have a lambda g term, right? So here are all of our m constraints. And more compactly, if you write this as a dot product, that's the dot product between the lambda vector, which will just contain lambda 1 through lambda n, lambda 1 m, and then the g of x vector, which will just contain g1. Notice we have a vector above the g, so that's just all of these m constraint functions. Now let's just consider the simple case of just one constraint. And so what we want to do is we want to minimize with respect to x. We want to find the x vector that minimizes the Lagrange function. Right? That's what we aim to do. And when we think about what we really are set out to accomplish is we want to really minimize the objective function. However, because we also have a constraint, we need to make sure that we restrict ourselves to regions that fall within the constrained region. And so what we can do here is we can think about the lambda as sort of a weight, or a penalty weight. And we can think about this as a penalty term. So we want lambda g of x, we want that to be 0 when we are inside of the feasible region, and we want it to be really, really large when we're outside of the feasible region. So let's define it this way. Let's kind of think about it conceptually as lambda g of x. We want it to be near 0 when x is in the domain of g of x. In other words, we're within the constrained region. And we want it to be infinite otherwise. So within constraint, outside the constraint. So the reason we write it this way is because we might think about the objective function as, let's say that f of x looks like this. And we'll say that this is f of x right here. Well, as we can see, if you're looking for a global minimum, the global minimum is clearly here, right? That's the lowest point on the curve, assuming that the function only increases in both directions. Now, what we're aiming to do here with the plus the lambda g of x is rather than to, let's say we're constraining ourselves to some region, let's say right here and here. So between there and there is maybe this is our constraint. So we're constrained between those two limits right there. So as you can see, that's between this point and this point, and you can see that within that constraint that the minimum actually lies right there. So by imposing the plus lambda g of x, what we're going to do is we're going to say that, okay, if you're within the constraint, if you're within that boundary, then you are dealing with this function right here. But if you're outside of that constraint area, then we're going to make that objective function essentially equal to infinity, right? So if you're outside of that region, then we're just going to pretend like, this is up here at infinity. So if you're within the constrained region, then you take on the value of f of x. But if you're outside of the region, then you take on the value of f of x plus this very large lambda times g of x. And so you're inflating the objective function when you're not meeting the constraint. And that's how you make a problem unconstrained. But of course, we want to make sure that our function is continuous. so that it has derivatives, right? Because this function, the way I've drawn it, doesn't have clean derivatives, right? It has holes in the graph, it has or breaks in the graph, and so this is not a continuous function. So rather than to do it that way, maybe with the lambda plus lambda g of x, we can sort of make it boost up to infinity relatively quickly, right? So maybe it looks more like this and then more like this. So we're going to inflate the objective function by this lambda g of x term if we don't satisfy the constraint. And we do it smoothly. So we're no longer dealing with the original function, but we're dealing with this really nasty sized function. And so if you think about what we want to do is when we use the Lagrangian and set its gradient to 0, we are doing so to help ensure there is a penalty for stepping outside of the boundaries. The penalty is so large that it ensures we do not find a minimum outside of the feasible region. So we want to minimize f of x plus lambda g of x, but on a maximal lambda. We want that penalty to be huge. We want to maximize it. So when you're dealing with mins and maxes, because f of x doesn't depend on lambda, that would be the same thing as writing minimize this function over all x, over the domain, but then with a maximal lambda of the function f of x plus lambda g of x. Again, the reason we can pull that max operator out is because f of x doesn't in any way influence the size of lambda. And this is called the primal problem, okay? And so you can think about this as the minimum with respect to x of the maximum with respect to lambda of our Lagrange function. And so that's why it's convenient to write it that way. And also, it turns out that if you maximize over lambda and then minimize over x, that this also provides some important information. In some cases, these are equal. In some cases, there's an inequality between them. But essentially, what we're doing is maximizing over lambda, minimizing with respect to x of the Lagrange function, okay? And that's called the dual problem. So we have the dual problem, we have the primal problem, and we're not going to get into the details of optimizing between them, but just be aware that there's two ways to phrase the problem that we're dealing with. Now, in order to guarantee optimality, when we form the primal or dual problem, we are implying conditions that must hold in order for us to find an optimal solution. So first of all, this condition right here says what we already do. We set the Lagrangian equal to 0, and we solve that. So the gradient of Lagrangian. Then we also have these constraints that are of the form g of x is less than or equal to 0. Of course, if we had multiple, we would just say g vector of x, and we'd have a vector of lambdas, put the lambda over our vector hat over the lambdas. Also, all of these lambdas we want them to be greater than or equal to 0 because we want to create penalties, right? We want the penalties to be big. We don't want to decrease the penalty by using negative lambdas. And then also we want lambda times g of x to equal 0. And this means that we are within the constraint boundaries, okay? Because in that case, we don't want to impose a penalty. And these are called the Karush-Kuhn-Tucker conditions, or for short, everybody just calls them KKT conditions. So not remember these three names, or these two names, I guess, Karush-Kuhn and Tucker. So we call them the KKT conditions. And these conditions are necessary for there to be a local optimum. But are they adequate? Is it enough? Well, no. If the optimization problem is also convex, then we have the necessary conditions and sufficient conditions. Sufficient means we have enough to guarantee optimality if that set or that problem is also convex. And that means that your objective function and your constraint are both convex. In a nutshell, convexity and meeting the KKT conditions make the mathematics nice. Okay, it guarantees optimality. That's all we're going to worry about here. We've mentioned it. Let's take a look at an example of working with this idea of convexity. So here I'm just going to state we have a convex optimization problem. Let's say that our goal, and like one of the many things we do in machine learning, is to predict something. So we want to predict the sale price of a house given measurable features. So let's say that we have n houses, each described by d features. In this case, we'll just say features, the size in square feet, number of bedrooms, age of the house, distance to the city center. We're going to build this design matrix, capital X, which will be an n by d matrix. And so what X will have in it is it'll have home 1 all the way through home n. So we'll have data on these n homes on the rows. And on the d columns, we'll have the size, number of bedrooms, age, and then distance to the city center. So this will be an n by 4, right? Depends on how many houses you have, but you're going to have 4 columns of data. Then we have a target vector, which we call y, and this is the actual recorded sale price for each house. So these two things help form our training data, right? We're going to train the model, and we'll see what we mean by that in just a moment, but the y vector will just be the actual prices of home 1 all the way to the sale price of home n. That's what that vector will have in it. This will be an n by 1 vector. And okay, here's what we want to optimize. We want to create some model parameters w on this linear model, and w will be a d by 1 vector. So basically it'll be a 4 by 1 vector, 1, 2, 3, 4. And inside of this vector, this d by 1 vector, we'll have these weights that will indicate how important each feature it is in contributing to the price. So as an example, maybe we want to place weights that sum to 1, and they don't have to sum to 1, but maybe we want to say, we think that size is going to be 80% of the value, and then 10% of the home value will be on the number of bedrooms, and then 5% on age and 5% on distance from the town center. Okay, that's forcing the weights themselves to sum to 1. Okay, often you want the size of that vector to be something in particular, and we'll see that in a moment, rather than the sum of the weights. But let's say that we multiply x and w together. Okay, well, if you take this w vector, which contains these weights, and you apply it over here, 0.8, 0.1, 0.05, 0.05, you can see we're going to be scaling size, bedroom, age, distance, and then summing them together, meaning that if we take a big weight and multiply it by size, ideally that term will contribute more to the value or the price of the home than some of the other values. Of course, size is probably going to be the biggest number, right? Because it's going to be in square feet, and you're going to have thousands of square feet. And so there are ways to kind of limit the effects of these weights. Okay, so x times w is the predicted prices from the linear model. It'll be based on the weights times the data. Y will be the true prices, and then xw minus y will be the residuals. It'll be prediction errors. It'll be the difference between predicted and true. And if xw minus y is large in magnitude, the model is making bad predictions, right? So not good. Okay, we're going to compute the Lagrangian, and the Lagrangian has to take into account our objective function. We'll come back to this identity in a moment to help us really quickly optimize this. So the way we're going to build this is we want the squared distances, as we've seen in linear models, we want the square distances to be minimized. And also, by the way, I'm going to put a 1/2 out here. And that's just all that is going to do is this is just a scale factor. And all that does, it's not going to change where your minimum occurs. Because remember, we're going to want to minimize f of x over the domain. And so if you take a function that maybe looks like this, 2, 1, and maybe you have a function that looks like a parabola, well, if you were to simply cut those values in half, it would just bump this point down, right? it would bump this point down to half of itself and this point down. So you're not going to change x for the minimum, right? So if that's the value of x naught right there, where the minimum occurs, then in both cases it occurs at the same point. The 1/2 is just going to make the mathematics just a little bit cleaner, okay? And then g of x are constrained. This is not going to seem obvious, but we typically in regression and in machine learning want the squared magnitudes of the weights to equal some constant, okay? So this just means that square magnitude is fixed to t. Okay, that's just the size of it. It could be 1, it could be 10, it could be whatever you want it to be. So I shouldn't call this g of x. G of x needs to be set equal to 0, and so it's actually going to be w squared minus t. So when you set that equal to 0, that's how you get your g of w. Okay, so what the Lagrangian will look like, the Lagrangian, therefore, of, in this case, our estimation is going to be of, sorry, I should have put w over here, not x. This will be the w naught, and same thing here. Okay, so that's just the name of the variable, and then we also have lambda. Okay, so this will be f of w. Again, I did it here. The reason I can't use x is because x is a matrix here, right? But we're trying to find the w that minimizes f of w. Okay, so we have f of w plus lambda times g of w. And so that's going to be 1/2 times the square of the magnitude of xw minus y, and then plus lambda times the magnitude of w squared minus t. Perfect. Okay. Let's now compute the gradient. But before we do that, because we have this magnitude in here, remember magnitude is the square root of, the magnitude of a vector x is x transpose x square rooted, right? Essentially boils down to Pythagorean theorem. And if we square that, then we just end up with the magnitude, the vector that we're trying to take the magnitude of, transposed multiplied by itself. So in this case, it'll be 1/2 of xw minus y transpose times xw minus y. And I'm going to do the same thing over here. This will be lambda, and I'm going to distribute the lambda. We'll have w transpose times w minus lambda times t. Okay, now what we would ideally need to do here is we would need to distribute this all out, FOIL, and you can do it that way, but it turns out that we have a neat identity for this, okay? Identity number 10 from when we looked at gradient identities says that the derivative with respect to s of a vector s of x minus matrix A times s times some w matrix, which is just any symmetric matrix, multiplied by x minus ax is equal to -2 times x minus as transpose times w times a. Now, the reason we wanted this 1/2 there is it'll cancel out this -2 when we do it. But we got to match things up, right? Because our thing is not quite the same. But xw minus y is the same thing as the negative of y minus xw. Okay, so if I pull out a -1 times 1/2, and I write this as y minus xw transpose, and then if I put an identity matrix here in the center, identity is always symmetric, right? Means if you take the diagonal, you look above and below it, you always have the same entries. multiplied by, and then again, I'll factor out a negative 1 from this expression, and it'll be y minus xw plus lambda w transpose, or lambda w transpose w minus lambda times t. Okay, now you see that the negatives cancel out right there, and you're just left with the 1/2. Okay, so gradient of L w comma lambda. The gradient of that first term, right? Look at this for a moment, where here they're using x, we are using y. Where they're using a, we're using capital X, and our s is actually the w vector. So yes, we are looking at the gradient is the derivative with respect to w, and multiplied by w, multiplied by the identity, which is our w, times y minus xw. And so what does that come out to? Well, it comes out to, we have the 1/2, which is the coefficient here, so I'm just writing that down, times the derivative of that, which will be negative 2 times y minus xw transpose times w. Okay, what's w? Well, w is the identity matrix for us, multiplied by A. And what is A? Well, A is our X matrix. So we didn't need to do any foiling. We got to use that property with just a little bit of manipulation. So that's going to come out to negative 1 y minus x w transpose times matrix X. Perfect. Okay, now we just need to worry about this last term. Okay, so for those derivatives, first of all, notice that we are taking when we're taking the gradient, it's the gradient over w. Okay, so everything else is a constant, which if you look at minus lambda t, that's a constant, right, with respect to w, so its derivative will be 0. Now the last thing that we need to deal with here is this lambda w transpose w. And there is also a useful gradient identity for this, and that's number 9 from our identities. And number 9 from our identities will be perfect here because we have variable transpose variable. And this says that the gradient with respect to x of x transpose times some matrix B times x is x transpose times B plus B transpose. Well, we don't have any constraints on what that matrix has to be. So why don't we just go ahead and say that our B is the identity matrix and our X is the W matrix. And so that's exactly what we're doing. We have a factor of lambda, but we can pull the lambda out, right? Because lambda is just a constant. So we'll have plus lambda. And okay, what's going to be the derivative of W transpose IW? Well, it'll be W transpose times I plus I transpose. And what does that equal? Well, that just equals W transpose times I because, hey, I is symmetric, right? So what would I plus I transpose equal? Well, let's just think about the 2x2 case. If we had 1, 0, 0, 1, and then you transposed it, you turn the columns into rows, 1, 0, 0, 1. Well, notice that's still the identity, and you'll just get 2 times the identity. Okay, so that means that we'll have times 2 times the identity. And again, 2 is a scalar, so if I factor that out, and again, I just have the factor of lambda. Don't forget we have the factor of lambda here. Lambda, and I'll just put the lambda over here. 2 times I is just, W transpose times I will just be W transpose. And so we'll get plus 2 lambda W transpose. And then we take that and we set the gradient of the Lagrangian equal to 0. And now we would solve for W. Okay, so we'll go ahead and stop there. This would require some manipulation and distribution, but the idea here is that this would give us the optimal W for which the minimality, in this case optimality, would hold for this problem. Now, to actually go about solving this, typically it's going to be some type of numerical method because these equations can get quite cumbersome with as many as there could be, depending on how big all of these vectors and data entries are.